So in our last video, we said we don't have this problem with addition and multiplication. So really it boils down to this theorem from your textbook, Theorem 2.6. So it says if the equivalence class of A is equal to the equivalence class B, and the same thing for C in some fixed numbers in Zn, then if I add A and C together, you get the equivalence class A plus C. If I add B and D together, you get the equivalence class BD, and these are the same. And also you get the same thing for multiplication. So if I multiply A and C together, you get AC. That's the same thing as if you multiply B and D together. So let's go over the proof of this. So we're going to assume the equivalence class of A equals the equivalence class of B, and C equals D in Zn. So we're going to start, the first thing we're going to prove is that these equivalence classes are the same. So what does it mean for these equivalence classes to be the same? So the end of our proof, we need, if the equivalence classes are the same, that means that n divides the difference of these two. So A plus C minus B plus D. So that's what we're going to work towards. So let's write down what these things tell us here. So if A is equal to B, that means A is related to B. So in other words, so since A equals B, we can say that n divides A minus B. The same thing for, because C is equal to D, that tells us that n divides C minus D. And so now we're going to convert, I'm going to erase this so we can save some room here. We're going to convert those two equations. There exists integers, let's go with K and T in the set of integers such that A minus B equals n times K and C minus D equals n times T. And now what we're going to do is we're going to add these two equations together, adding these equations gives, so you're going to get A plus C minus B minus D equals NK plus NT. And this is almost what we needed. So what I'm going to do is I'm going to factor out the minus on the two terms on the left, and then factor out an n on the right. And what does this say? This says that n divides A plus C minus B plus D, which is exactly what we needed to say the equivalence class of A plus C is equal to B plus D. So we got half of our proof done. If we look back, we now have established this summation formula. So now we need to work on this product. So let's think about what we need for this product. We need, if these equivalence classes are equal, that means I need n to divide. So let's leave some space here. I need n to divide AC minus BD. This is what we need to get to. So we need to start with AC minus BD. So what we're going to do is we're going to expand this out. We're going to subtract BC and add BC. So essentially what we did is we put in a 0. We put in 0 because we added in BC, but we also subtracted it away. And so the reason we do that is because if you look here, in the first two terms, they have a C in common. And so you can factor that C out. And then if you look at these last two, they have a B in common. So you can factor that out. And now, what do we know about A minus B? We know that this is N times K times C. What do we know about C minus D? It's N times T. And so you can factor an N out here. So what did we learn? That this is N times something, so N has to divide AC minus BD. And this means that our two congruence classes are equal. There. Okay, so that's the end of our proof. So again, why is this theorem so important in terms of our operations? So what it's saying is that our definition of addition and multiplication is independent of the choice of representative from each congruence class. So it doesn't matter which representative you use for your congruence classes, you're going to get the same answer when you compute addition and multiplication.